use those things to simplify the system. Right? So let's just recall what the legal operations were. So legal in the sense that they do not change the solution set, or in other words, they produce equivalent systems. They result in equivalent systems. Okay, so let's recall what they were. What were the legal operations? The first was, I think, switch, right? Switch their order. The second was multiply by a non-zero scalar. And the third was to add one equation onto another. Okay, to add one equation onto another. And if you think about it, you could say multiply one equation by a non-zero scalar and then add it onto another. Right? That's just a combination of 2 and 3. So you might as well say add a multiple, add a non-zero multiple. Actually, you could add a 0 multiple. That's fine, right? Nothing would happen. So add a multiple of one equation. Add a multiple of one equation onto another. So if you do any of these things, then the system doesn't change. Right? I mean, the system that you get is going to be equivalent. Okay. So going back to the system that we had last time, 3x plus 2y plus z equals 39. 2x plus 3y plus z equals 34. X plus 2y plus 3z equals 26. You could take the system and so what I'm going to do is just for the heck of it, and you'll see why I'm doing this later. I'm going to move this guy to the top. Okay, so I'm going to switch rows 1 and 3. Let me write this row 1. I'm going to switch with row 3. 3x plus 2y plus z equals 39. 2x plus 3y plus z equals 34. Okay, and then what I'm going to do is I'm going to take -2 times the first row and add it onto the second row. Okay, so row 2 is going to turn into row 2 minus twice row 1. Okay, and I suspect that there may be some error. I kind of remember that there is some error in my notes, but I don't care. Okay, so 3x plus 2y plus z equals 39. Right? And then I'm going to do the same thing. I'm going to take -3 times this guy and add it onto this guy. Right? I'm going to keep on going like this. Okay, so I'm going to get x plus, so row 3 becomes row 3 minus 3 of row 1. Negative y minus 5z equals negative 18. Negative 4y minus 8z equals negative 39. Right? And then I'm going to say take -4 of the second row and add it onto this guy. So I'm going to take make the third row turn into, I'm going to add on -4 of the second row onto the third row. Right? And you end up, I hope, otherwise I kind of have a feeling that there is some error. But it doesn't matter, the idea is correct. 18 and 12z equals 33. Okay. So you take your system, and then using the legal operations, you simplify it down to what's called a triangular system, right? And then at this point, you say, okay, well, from this point, it's easy to solve, right? I can figure out what z is. Z is 33/12. Once I know what z is, I substitute that back into here. I can figure out what y is, and I figure out what y is, and I substitute both z and y back into here, and I figure out what x is. Okay, so once you reduce to a triangular system, then it's easy to solve, and you say, okay, then I've solved this system, and I know that the solution set is the same. So the solution set here, which I think turns out to be x turns out to be 111 over 12, y turns out to be 51 over 12, and z turns out to be 33 over 12. So this thing has this unique solution, and you know that because you've only used legal operations, that's the same for this original system. This original system has a unique solution, namely that one, the same as that. Okay, so this process is called solving. This last part is called solving by back substitution. It's not. Don't worry. I doubt I will ever say this again. Substitution. It's not that important a phrase. Solving by back substitution. Okay, everyone all right with that? It's not particularly exciting. I'm afraid that most of today's class will be along the same lines. Not particularly exciting. Okay, so more terminology. So terminology here. When we say an m by n linear system, what we mean by that is a system of n equations and n unknowns. So this is a 3 by 3 linear system, right? Three equations, 3 unknowns, right? If m is bigger than n, we call it overdetermined. Overdetermined. If you have more equations, right? If you have more equations than unknowns, then it's called overdetermined. If you have fewer equations than unknowns, it's called underdetermined. Other terms that are again not that interesting. A square system, so obviously m is equal to n. 3, strictly triangular system. Strictly triangular system is like the one we have here, right? In the first equation, the coefficient of the first variable is non-zero. In the second equation, the coefficient of the second variable is non-zero. In the third equation, the coefficient of the third variable is non-zero. Okay, in other words, it's a triangle. Right? So yeah, that's it. So by strictly, they mean that it's not something like this. Okay, they would call this a triangular system, but not a strictly triangular. So strictly triangular really means that it actually is a triangle. It's not important. Okay. But observe that. So remark. If I write RK means remark. Any strictly any square strictly triangular system has a unique solution, right? Because if you're strictly triangular system, you're like this, and then you just do back substitution, right? So just by back substitution, you'll have a unique solution. So you remember that we said that there are three possibilities, right? You can have one solution, no solutions, or infinitely many solutions. So this is saying that you're always going to be in the case of having a unique solution. Okay. Any questions so far? No, right. Okay, so another sort of non-interesting observation. So another, in my notes I have another mediocre observation. Another mediocre observation is that one could just use the numbers, right? Instead of writing x, y, z, right, you can just use the numbers, right? You can say 3, 2, 1, 39, 2, 3, 1, 34, 1, 2, 3, 26. Okay. You could make this matrix of numbers, right? And that's what one usually does. This thing here on the left, okay, so this thing here on the left is called the coefficient matrix. And I always abbreviate, whenever I write mx, that means matrix. This whole thing here is called an augmented matrix. And then the operations, the legal operations that we did are called the elementary row operations. Elementary row operations. Okay, and you recall at one point we had something like this: 1, 2, 3, 26, 2, 3, 1, 34, 3, 2, 1, 39. And then we used this 1 to turn this 2 into a 0. We used the 1 to turn the 3 into a 0, right? Right. This thing, in that case, you call the row that you're doing this with the pivotal row, and you call this thing the pivot. It's just terminology. This thing that you use to clear out the coefficients between it is called the pivot. Okay. So just terminology. Okay, so that's let's move on. Okay, so let's go back to something that we were looking at the first day. So recall on the first day we had some system. We said, what happens if we go back to elementary school? And then we look at these systems, and we had one system which reduced to a single equation. Right, a single equation. Right, it turned out that both of the equations were the same equation. Right, so there were two lines that just overlapped each other. It reduced to, I think, x plus 5/3 y equals 2, right? And it had infinitely many solutions, infinitely many solutions. Okay. So one way of describing the solution set is to do this. You solve for x. You say, well, x is going to be 2 minus 5/3 y. Right? any point of the form 2 minus 5/3 y, 5/3 1, comma y, where y is any number, will do. So this is like a parametric way of describing the solution set, right? You could, I mean, geometrically, you could just say, well, any point that satisfies this, right? Any point xy such that this is trig, right? But you maybe make a cleaner description by solving for x and noticing that this could be described as a one parameter, as a family of points that depends on a single parameter. Right, so now I can generate points. You know, I'm sure you can generate points easily from here, but even more easily from here, right? I could say, well, 2, 0 lies on this line. Well, you know, -3, 6 lies on this line. And you can just choose whatever y you like, and you generate all the points. Okay. So that is if I take any point t. 2 minus 5/3 t, t is the solution set. When I look at all the points of the form 2 minus 5/3 t, comma t, whereas t ranges over the real numbers, then that's the solution set. You could, I wasn't thinking to do this, but you could even make it a little simpler. You could say 2, 0 plus t times -5/3, 1. Right. This is maybe another way of describing it as t ranges over the numbers. Right. Just using vector addition, right? Scalar multiplication and vector addition, expressing this as a combination of vectors. You've got this one vector, and you've got multiples of this other vector. And those guys are the solution. Don't worry. Anyway, all I need to say is that you can describe the solution set in a couple ways. Okay, everyone all right? Anyone have questions? Nope? Okay, good. Okay, so now from there, let's go to another system. So we're pretty much in 1.2 now, called row echelon form. So suppose I give you this system, 2, -4, 2, -2, 0. 2, -4, 3, -4, 0, 4, -8, 3, -2, 0, 0, 0, -1, 2, 0. Okay? So four equations and 4 unknowns, right? This is really 2w minus 4x minus plus 2y minus 2z equals 0, etc., etc., etc. And so you've got 4 equations and 4 unknowns. And I say, I'd like you to solve this system, right? First off, can anyone tell me one solution to this system? 0, 0, 0, 0, 0. Right? So you notice that the numbers over here are all 0. This is what's called a homogeneous system. Right? Homogeneous systems always have at least one solution. Right? 0, 0, 0, 0. Will do. Okay. So yeah. So what would you do to solve this system? Say? Well, what moves would you make if we wanted to simplify this system? Yeah, Anna.
Yeah, we just subtract the first equation from the second one.
Okay. Yeah.
So we get to eliminate the first two variables.
Okay. So we'll add on -1 times the first onto the second guy. So row 2 becomes row 2 minus row 1. So it becomes 0, 0, 1, -2, 2, -4, 2, -2. And maybe you do something similar right after that. You could take this guy minus twice that guy. And so I'm gonna do two steps just to save time. Let me do 2 steps. Right? So I'm gonna then I'm gonna do row 3 becomes row 3 minus 2 row 1. 2, 4, 2, 2, 0. 1, 0, 0, 1, 2, 0. And then that minus twice that is going to be 0, 0, that minus twice that is going to be -1 minus 2, 0. 0, 0, 0. Okay. Maybe just for convenience, I'm going to divide the first one by 2. So row 1 becomes a half of row 1. I get 1, -2, 1, -1, 0, 1, -2, 0. And you notice that I can use the second row to kill off the other 2 rows. Right? So I'm going to just do that right now. So these are all 0. Okay, so all we've done is use the legal operations, right? And we end up with this system, right? X1 minus 2x2 plus x3 minus x4 equals 0, and x3 minus 2x4 equals 0. And just a terminology. This process of reducing down to a form where you've got 1 as the first thing in each row, and then you've got more and more zeros and then 1s, this sort of thing, is called Gaussian elimination. So this process is called Gaussian elimination. This sort of form is called the row echelon form, row echelon. So Gaussian elimination, you take your matrix and reduce it to the row echelon form. These guys corresponding to the ones are called the lead variables. The lead variables. And then the other ones are called the free variables. So lead variables here are x1 and x3. The free variables are x2 and x4. Those are just words. In any case, what you do is you take your matrix and you reduce it down to something simpler, whose solution set is easy to write down. Okay, so what's the solution set? What's the solution set? Right. Well, we have x1 minus 2x2 plus x3 minus x4 equals 0. x3 minus 2x4 So the way one solves for this, the way one gets the solution set is to keep the lead variables on one side and move the free variables to the other. So you say x1 plus x3 equals 2x2 plus x4, x3 equals 2x4. So what you see is that the lead variables can be expressed in terms of the free variables. The lead variables can be expressed in terms of the free variables, just like when we had this x plus 5/3 y equals -2, right? We expressed x as -2 plus 5/3 minus 5/3 y. Right? Or maybe there's a minus here. Okay, so right, you take one variable and express that in terms of the other variables, and what we see here is that we're going to end up with a solution set with two parameters. Right, a two-parameter solution set. In other words, it's going to be a plane. We're going to have a plane of solutions, a full plane of solutions, right? In our four-dimensional space, we'll have a plane, a two-dimensional plane of solutions. Okay. So you see what you do, right? Via back substitution. Although I said I would never say it again, here I am saying the phrase back substitution. Sorry, I didn't think I would. Via back substitution, you say, okay, well, you know, x1 plus 2x4 equals 2x2 plus x4. In other words, x1 equals 2x2 minus x4, right? And x3 is 2x4. So we have expressions for the lead variables in terms of the free variables. And then we just write it down just like we did over here. Just like we did over here. So any point of the form 2x2 minus x4, x2, 2x4, x4 is a solution. Where x2 and x4 can be any numbers. Right, so we can generate solutions as we please just by choosing any pairs of numbers x2 and x4. And then just seeing what you get. And often one rewrites this. So one often rewrites this as, say, some number times. So let's use r for x2. So 2, 1, 0, 0 plus s times -1, 0, 2, 1, where r and s can be any numbers. Right, so you use your knowledge of vector addition and vector arithmetic to express this as this thing will be expressed as a combination of multiples of these two vectors. Yes, same.
So where are you getting the x2 to x4 and the x4? I understand how you got x1 in terms of x2 and x4.
X2 is just x2. I just leave it as is. Right? Okay. Your point looks like x1, x2, x3, x4, and it must satisfy this. It must, right? Your solutions are any point x1, x2, x3, x4 that satisfy this. Well, to satisfy this, x1 must be 2x2 minus x4, and x3 must be 2x4. So that tells you it must be any point that looks like this, where x2 and x4 can be whatever they feel like. and x1 and x3 depend on.
Okay, so you have to modify or you have to put the lead variables in terms of the.
That's right.
Okay.
That's right. And that's a little bit arbitrary, to be honest, because if you reordered your system, then maybe x1 would be the free variable and x2 would be the lead variable. So there's a little bit of arbitrariness there, but yeah, but it'll work out. It works this way. It will work just as well the other way if you reordered. Yeah. But what will always happen is you'll end up with, it would be a two parameter system of solutions. No matter how you can't just reorder it and end up with a completely different solution set, say. Okay. Everyone all right? Any questions? Okay. Maybe that's a little bit interesting. Okay. So just one remark. We could have continued one step further in the process. And this is a very dumb remark. So from here, we have 1, -2, 1, -1, 0, 0, 0, 1, -2, 0. You could have gone one step farther and gotten this, right? And then, right, you would have gotten that, immediately you would have gotten that x1 equals 2x2 minus x4, and x3 equals 2x2, right? So that would have just done it for you. You know, if you had used this pivot to clear out above as well as below, then you wouldn't have to go through the back substitution. It's just, you know, whatever you want to do. If you want to stop there and then do back substitution, or you want to go here and then use this thing to clear out above, it's actually the same amount of work. So you know, it's really up to you. But you know, sort of regrettably, this is given a name, Gauss-Jordan reduction. Why? So, like, the previous thing is called Gaussian reduction, and then if you do this last step, it's called Gauss-Jordan reduction, which is a real sort of blight on Mr. Jordan's name. Right? I'm sure he is a great mathematician. In fact, if he is who I think he is actually a very great mathematician. But his name is associated with this very minor step. Okay. Okay. Does that make sense? Is that clear? I'm just saying that you can do the back substitution while you're doing the row operations. Okay. Okay. So this leads you to sort of an observation. If you have an underdetermined system, that is something like this, where there are more variables than equations. Right? You have too few equations. If you have an underdetermined system, then sort of like it's usually consistent. It's usually consistent. Right? Who knows? Maybe you end up with some contradiction, but usually it's consistent. And if consistent, then we'll have infinitely many solutions. Right? Like, because if it's consistent, you're going to end up with something like this, where you've got a solution set with some parameter, with some free parameter. Right? You're going to end up with infinitely many solutions because of the existence of free variables. If you've got a free variable and you have a consistent system, then, well, you've got infinitely many solutions. Okay, so that's just an observation. Okay. So in consequence, any underdetermined homogeneous system automatically has infinitely many solutions. Has infinitely many solutions, right? Because if it's homogeneous, if it's a homogeneous system, then you're guaranteed a solution. And if it's underdetermined and has a solution, then it has infinitely many. So, just logically speaking, you're guaranteed infinite many solutions. Anyway, so that too quickly. So the first thing says, if you're underdetermined and you have a solution, then you've got infinitely many solutions. If you're underdetermined and homogeneous, then you're guaranteed a solution, right? 0, right? So that means that you're underdetermined and consistent. So you're guaranteed infinitely many solutions. Okay. So nothing, not particularly inspiring. Okay, so let's go on. Any questions about this? Not particularly exciting, perhaps. Maybe I should stop talking about how unexciting it is, but it's true. It's true. I'm not going to lie to you. Okay, so maybe we can get to something interesting. Whoops, let's see. Point basic matrix notation. It doesn't sound helpful. And algebra. Okay, so start off. What's a matrix? What is a matrix? Well, it's simply an array of numbers. An array of numbers. Okay, so you've got something like alpha 1, 1, alpha 1, 2, alpha 1, 3, up to alpha 1, n, alpha 2, 1, alpha 2, 2, where each of these alpha ij's is some number. Alpha 2, n, blah, blah. Alpha m1, alpha m2, alpha m3, alpha mn. This is usually how it's notated. So one abbreviates this as alpha ij, as I goes from 1 to m, and j goes from 1 to n. So this is a m by n matrix. Right? N is the number of rows. This is the number of columns. And one usually abbreviates, one usually uses some sort of capital letter to abbreviate, to represent the whole thing. Okay. And, one writes A lies in R m cross n to say that you're an m by n matrix, okay? Or A lies in cursive m, m and R. So you're in the matrices that are m by n, and each of the entries is that you?
Sorry.
Each of the entries is a real number. Okay, so it's a matrix. At least for now, we're going to deal with we'll deal with matrices of real numbers. Okay. Okay. So some particular cases. Note it's an m by 1 matrix. We'll also call it a column vector. It was sort of mix up the notions of vector and matrix, right? So it will be something like this: A11, A21, AM1. Right? It'll be a vector. If it's a 1 by n matrix, it's also called a row vector. We'll sort of allow ourselves to mix those things. Some basic definitions. One, when our matrices equal to each other, we say A equals B. If you have two matrices, A and B, we say they're equal if A and B are the same size. Okay, they have to be in the same size, so same size. And two, if alpha ij equals beta ij for all I and j. So all the entries must be equal. So it's just saying that they're the same size and everything is equal. Okay? So if you have something like this, it's not equal to this. Because they're not the same size, even though the entries that exist are equal to each other. Okay. So it has to be the same size and the entries have to be equal. Okay. Number two, how do we define vector matrix addition? So addition. Let's say that A and B are the same size. It's sort of what you expect. We define A plus B to be the matrix, the m by n matrix with entries gamma ij equaling the sum of the corresponding entries. Right? So you just sum the corresponding entries, right? So 1, 2, 3, 4 plus 1, 0, 0, 0 is going to be 2, 2, 3, 4. Okay. Right? You just sum component-wise, just like you did for vectors. Okay. Scalar multiplication. Scalar multiplication, right? Just like when you did calculus 3, maybe you multiplied vectors by scalars. If you have a vector, if you have a matrix and you have some number, then we define CA, right? The number times the matrix. You can probably tell me what it is. Like what do I mean when you multiply a matrix by a number?
Multiply all the terms in the matrix.
Just multiply all the terms by the identical number, right? So so by so let's say that this thing is gamma ij by C alpha ij, right? So you take all the entries, so for all I and j, right? So for every entry, you take the ij entry from A and you multiply by C, right? So not easy, right? So 2 times 1, 2, 3, 4. Just multiply everything. 2, 4, 6, 8. We didn't make it. So I was hoping we'd get to matrix multiplication, but I guess we're going to end on a low note. That's okay. So the zero matrix, right? What's zero? It's simply the matrix of the appropriate size with all entries equal used the upside down A a couple times. Upside down A means for all.
Oh.
So this is 0 for all I and j. And to end on, as I promised on the moment, the additive inverse, negative A, the thing that you add to A to get the 0 matrix is, of course, negative 1 times A. Okay, yeah. Negative A, the additive inverse of A is you get it by taking the number of negative 1 and multiplying it by. See you guys next time. Right? The additive inverse is that which you add to A to get 0. And in this case, it turns out to be what you think it is. Okay, yeah. Hope to see you next time. If that doesn't scare you away, you will never get scared away. Okay, so next time, something good, matrix multiplication.